Okay, yeah. So I'm super excited to be here today to kind of introduce to all of you a little bit of what we can do for exoplanet spectroscopy at high resolution. So I'm going to be mostly focusing this talk around a large program I'm leading with iGrins, but along the way, I'm hoping I'll give you a little bit of background on, in general, how we do exoplanet spectroscopy with high resolution instruments and some of like why we're interested in studying this. All right, so first, why are we interested in studying the compositions of exoplanet atmospheres? So there's a wide variety of different reasons. We want to eventually do things like look for gases that could indicate habitability or signs of life in small planet atmospheres. But today I'm going to be talking about hot Jupiters, large hot gas giant planets, where one of the big questions that we want to answer is how did these planets form and how did they end up in their current close-in orbits? And one of the ways we can investigate this is by measuring their molecular abundances. So specifically here, I'm showing a plot looking at the carbon to oxygen ratio as these planets are forming. So the idea in this plot is as you go out from the star in the protoplanetary disk, the disk is going to get colder and various molecules like water and CO and CO2 will condense out from the gas into solid grains in the disk. And so depending on where your planet forms and whether it's mostly accreting solids or mostly accreting gases, you can get a different carbon to oxygen ratio in the atmosphere of that forming planet. So the idea is now if we take observations of hot Jupiters and we measure the carbon to oxygen ratio, we can kind of back out this information on where these planets might have formed. So the problem with previous measurements to look at the carbon to oxygen ratio in these hot Jupiter planets is that they've really been limited by low wavelength coverage and low resolution. So one of the premier instruments that has been used to look at hot Jupiters is the Wide Field Camera 3 on the Hubble Space Telescope, which I'm kind of showing that wavelength range here. So this instrument's been really great for looking at, in particular, the abundance of water in these planets' atmospheres. But it has a pretty restricted wavelength range from about 1.1 to 1.7 microns and observes at a resolution of only around 50 to 100. So with that resolution in that wavelength range, essentially what we can detect in these planets' atmospheres is a single broad molecular band of water and no real carbon-bearing species. So if we compare that instead to studies from the ground, so today I'm going to be talking mostly just about iGrins. iGrins covers this wider wavelength range where we can see features of a wide variety of molecules, water, OH, CH4, CO, basically everything we think should be major carriers of oxygen and carbon in these planets' atmospheres. And additionally, iGrins has this much higher resolution. So instead of just seeing one broad absorption band feature, we can resolve all of these individual lines, which give us a much better handle on what the actual composition of these planets are. So I'm currently leading a survey to measure the transmission spectra of 11 different exoplanets with iGrins, with the idea being in this survey that we're looking at planets, I've plotted them all here, with a wide range of different parameters like mass, temperature, and age. So we're going to measure precisely the abundances of all of the major carbon and oxygen-bearing molecules in these planets' atmospheres, and measure the C/O ratios for all these planets, and then be able to look at how that ratio depends on some of these key planetary parameters. We're also hoping to, in the future, combine this data set with other existing data sets for these planets, like those from space with Hubble and Spitzer, as well as ground-based data at high resolution at optical wavelengths to get a better holistic idea of what's going on in these planets' atmospheres. So today I'm just going to be focusing on one data set that we've taken from this program, and that's for the hot Jupiter WASP-76b. So just to give a little bit of background on this planet, it's what we refer to as an ultra-hot Jupiter, which means it has a really hot temperature around 2200 Kelvin. And because it's so hot, it was actually predicted that in the atmosphere of this planet, water would be dissociating and breaking apart into hydrogen and oxygen molecules. And indeed, it was observed with the Hubble Space Telescope and observed to have a black body-like spectrum, which indicates that it was being impacted by water dissociation. It's also been observed at high resolution before, and one really interesting result was that it was observed to have an asymmetric signature of iron absorption in its atmosphere. So the idea that the team proposed who made these observations to explain this is that it may have a hot spot that's slightly shifted towards one side of the planet because the planet's being heated primarily on one side facing the star, and then winds kind of shift that warmest spot around the planet. And in that spot, it could have vaporized iron, whereas on the cooler areas of the planet's atmosphere, that iron would condense out. So by having this kind of shifted spot where you get vaporized iron throughout the course of the transit, you could produce this asymmetric absorption signal because one limb has more vaporized iron than the other. And then it's been observed several times at high resolution, and there have been a lot of detections of various other molecules and atoms in this planet's atmosphere. Some examples are OH, several metals like magnesium and iron. But importantly, a lot of these have only detected these molecules and atoms and not really constrained their abundances. So that's what we wanted to do with these IGRINS data. All right, so we observed a single transit of WASP-76 with IGRINS this past October. So to start our data cleaning process, we just removed all of the orders that had a lower signal to noise. Here I'm just showing the signal to noise from one of the AB pairs that we observed. So we really get a lot of signal to noise for these planets because we're trying to see these very small signals of the planet hidden in this stellar data that we're getting. All right, so our goal is, so we want to detect this signature of this planet. And like I said, it's very small compared to the amount of light that we're getting from the star itself. Luckily for us, the planet is orbiting as we're observing it. So that means that because of the change in its radial velocity, it's going to have a slight shift in the wavelength of any lines from the planet over the course of our observation. This is kind of the key to how we separate out exoplanet data from everything else that's going on at the telescope, is that the planet signal is the only thing that's going to be changing in velocity significantly over the course of our observations. Unfortunately, this signal is completely drowned out by the star, the instrument throughput, and tellurics. But again, all of those are relatively stationary in wavelength over the course of the transit that we're observing. So what we do to remove those is we use a principal component analysis. So if you've never done a PCA before, the way that it works is it essentially identifies axes along which most of your data lie. So here I've just got a little cartoon showing an example. So let's say you're measuring heights and widths of a bunch of different fish. And maybe you have some small fish and maybe you have some large fish, but if they're all the same species of fish, then you might expect there to be some relationship between their height and their width. So as they grow, both the height and the width increase proportionally. So in that case, you'd measure these red data points here, and then if you applied a principal component analysis, the first component to come out would be the blue line running through those data. So it identifies that you've got this trend between height and width, and you could say, oh yeah, now we can tell all of these fish are just different ages of the same species. So we're essentially doing the same thing with our data, finding all of the things that we have in common in between different exposures and in one exposure at different wavelengths. So here I've just shown one data set here. I've picked out these two different plots here on the left. You can see just a few of the orders that we're observing with IGRINS in wavelength. And the main features you can see are the throughput, and then we have some tellurics in this leftmost order. And then basically every other feature you can see with your eye is from the star, not from the planet. And then I've also plotted a single point from one of these data sets over the course of our observations. So this is in terms of orbital phase of the planet or time throughout the night, and you can basically see a trend in air mass. So all of these trends are going to be essentially constant over the course of our observations, whereas our planet's signal is going to be the only thing that's changing in wavelength. So if we apply this principal component analysis, the first few components identify all of these signals from the tellurics and from the star and from the instrument, and we can subtract all of that out and we're just left with the planet signal. So this plot on the right kind of shows how that process works. So here I'm just showing on the top our raw data before we've applied this PCA. So you can see that we really can't see anything from the planet at all. And then as we subtract out more components, we get rid of more of this stuff from the star and from the instrument, and we're just left with the planet afterwards. So then once we've gotten rid of everything except our planet, we use a cross correlation with a model template to detect the actual signal from our planet. So there's kind of two types of plots people usually show in exoplanet work, and I apologize, we're not very inventive at naming our plots. But the first is called a trail plot. And the idea here is we are cross-correlating separately with every different exposure. So if we correctly detect the planet, we should be able to see the peak of that cross-correlation at different velocities as we're observing, because the planet's shifting. So indeed, we are able to see I've kind of highlighted here to guide your eye, this diagonal signal is from the planet. And then the signal that stays pretty constant in velocity throughout the night is actually from the star. We've got a little bit of leftover stuff from the star, which I'm not going to talk about too much in this talk, but I'd be happy to answer any questions about it. All right, so then the second type of plot that you'll see in exoplanet papers is called a blob plot. So basically what we're doing here is taking this sped up signal in this trail plot and summing it all up into one point in terms of the systemic velocity of the star on the x-axis and the Keplerian velocity on the y-axis. So again, to guide your eye here in white, I've put what are the expected values for these velocities for this system based on previous radial velocity observations. So you can see we get this peak in the cross-correlation signal near where we expect, which is how we know that we've detected this planet's atmosphere. All right, so then we can do this for a bunch of different gases individually to see what we can find in the planet's atmosphere. So we found detections, I'm showing here for water, CO, and OH in this planet's atmosphere in our IGRINS data. We also searched for a lot of other molecules that have either been found in this planet, suggested to be in this planet, or found in other hot Jupiters before. But we didn't find basically any of these other molecules. I'm just showing some examples here. So we just found those three primary molecules in the data. All right, so now we know what molecules are in our data. What we really want to do is constrain their abundances so we can get that carbon to oxygen ratio out. So the way that we do this is we take models for this planet at high resolution, and then we kind of add back on noise from our principal component analysis, everything that we took out of the planet signal, like the tellurics and everything from the star and that, and then run that model through the same PCA that we applied to our data. So that way we can kind of compare apples to apples, because maybe we did some weird subtraction on our data with the PCA, maybe it didn't work perfectly, it left a bit of the stellar signal behind. But then if we apply the same process to our model, we'll get out something that has the same inconsistencies, I guess. So then we can compare them. So in this way, we can do an atmospheric retrieval and actually constrain the abundances of these gases in this planet's atmosphere by comparing which of these models fits our data best. So here we were able to constrain the abundances of all three of these molecules that we detected really well with just a relatively simple atmospheric model fitting for these three molecules and then also fitting an isothermal temperature profile. So if we just take these values at face value and calculate a metallicity and a C/O ratio for this planet from those, what we get is that we have a metallicity that's consistent with solar, but a significantly supersolar C/O ratio of about 0.96. That's pretty high for what we expect for an exoplanet. That would be pretty strange. So we wanted to investigate whether this is really what's going on in the planet's atmosphere, or is this somehow being driven by the assumptions that we're making in this model. So to kind of put these measurements in context a little bit more, here, these points I'm showing are comparing the abundances we derived for these three key molecules to these lines in the background, which show the abundances that we'd expect for an atmosphere in equilibrium with solar metallicity and C/O ratio. So you can see that the abundances that we derive for OH and CO are pretty much consistent with what we'd expect for a solar composition atmosphere. And the reason we're deriving this high C to O ratio is because the water abundance looks depleted compared to what we'd expect from this model. However, if you look at this model, you can see that as you go up through the planet's atmosphere, the water abundance changes significantly. And what's happening there is actually what was detected for this planet with Hubble. The water is dissociating as you go higher up into the hot parts of this atmosphere and is turning into OH and atomic oxygen. So you can see that the OH abundance increases and then decreases again, and that oxygen abundance increases as well as you go up through the atmosphere. So to see if this water depletion that we're getting from our models is driven by this water dissociation in the upper atmosphere, we're working on upgrading these models now to allow non-uniform abundances throughout the atmospheric profile, as well as non-uniform temperatures. All right, so this was kind of a whirlwind summary of how to do exoplanets at high resolution. But I wanted to point out that this is just the first preliminary result from this survey. We've observed 5 of the 11 planets in our program, and we have another year left in this program. There's also a lot of other exciting exoplanet work going on. Jake Turner is going to talk about using GRACEs for exoplanets, and there's other large programs on IGRINs as well as MaroonX to look at exoplanet atmospheres. So it's really an exciting time to be studying these planets. So before I end, I also just wanted to point out that there's a lot of really interesting synergies that can happen between Gemini and high-resolution studies of exoplanets and JWST. So one that immediately comes out that people talk about a lot is that the way that we process these data that we get from the ground, we actually remove all of the continuum information. So we get information on relative strengths of absorption features, but we don't get any absolute information. So by observing these planets from space as well, we can actually add back in that continuum information. And like is being shown in this plot here, if we combine low resolution and high resolution data, we can get tighter abundance constraints than we'd be able to get from either data set on its own. And then there's also lots of other synergies as well. I just want to talk about one more that I'm very excited about, which is starting to understand a little more about the 3D structures of hot Jupiter atmospheres. So one thing that JWST is going to be able to do that we can't do from the ground is eclipse mapping of hot Jupiters, which is essentially a technique to get a 3D temperature map on the day side of these planets, resolved in longitude, latitude, and altitude. But this whole temperature map is presumably being driven by winds in the planet's atmosphere. And at high resolution from the ground, you can measure those winds directly based on red shifts and blue shifts in the lines that you're observing from the planet. So I think this is a really interesting area where you could combine temperature maps from space and wind speed measurements from the ground to really get a lot more information on the dynamical processes happening in these planets' atmospheres. So finally, before I end, I just want to acknowledge a few people, all of the co-Is on this program, all of the Gemini and IGRIN staff, especially I want to point out Greg Mason, Puyun Kim, who have been really helpful in figuring out how to use this great instrument for exoplanets. Exoplanets have a lot of weird requirements, so it's been very helpful having their advice. I also want to acknowledge funding from a NASA Sagan Fellowship, and respectfully acknowledge that the Gemini South Telescope is located on Cerro Pachon, which is in the traditional territory of the Diaguita people. And I'm very grateful for the access that we had to this site today to get these incredible data. All right, so just to conclude, so we detected water, CO, and OH in WASP-76b using IGRINs. Our first retrieval results suggest that this planet may have a solar metallicity, but a significantly supersolar C to O ratio. But we're currently looking into upgrading our models to see if this result is really true for this planet or depends on any model assumptions such as constant abundances in the atmospheric profile and the constant temperature that we were fitting. We're also going to be looking in the future into seeing if we can detect any limb differences, such as was seen on this planet with iron in the past. And this is just the first result from this survey, and there's lots of exciting surveys happening on the ground now with the Gemini telescopes. So I'm sure that soon you're going to be hearing about a lot more awesome exoplanet results with Gemini. So thanks so much, and I'd be happy to take any questions.
Okay, thank you, Megan, for a wonderful talk that was gloriously on time. Well done. Do we have any questions in the room? Let's start with Jake.
Great talk, Megan. Thank you for introducing this to everybody. And so can you go through how you correct for the star?
Yeah, so basically the star for the most part gets removed by the principal component analysis because it's mostly stationary. At least at the resolution of Igrins, it has about 2.5 kilometers per second resolution. So we can't see the star moving over the course of the transit. This little bit of stellar signal that you can see left in here is basically because of something called the Rosita-Mclaughlin effect, which is that as the planet transits the star, it's going to be blocking different parts of the star that are, because the star is rotating, red shifted and blue shifted differently. So you do get a little bit of a shift in the net velocity of the lines from the star. So we haven't actually explored correcting for that yet. For now, we're just masking out that stellar signal, so it doesn't affect our data, but that would be an interesting thing to look into in the future.
Hui, do we have anything online?
Yeah, we have 2 questions now. So David Drilling, who is in the room. On the pressure abundance plot, your points were near 10 to the minus 2 bar. And you said maybe they should even be higher, up at 10 to the minus 3. Why are you sensing the atmosphere at such a low pressure? I would have thought it would be deeper, where I guess the tau, like equal 1 level would be. Maybe my intuition is totally wrong. That's
Yeah, that's a good question and something that I can't answer in detail right now. But so for low resolution infrared observations for these hot exoplanets, typically the photosphere is around 10 to the minus 2. But we can see higher up in the atmosphere at high resolution, we see like a little bit more of a range of pressures in here. So I don't know exactly where the photosphere is for these data. I kind of just plopped these points down around where is reasonable. But we should be seeing a range of pressures there with the different line strengths that we're seeing, which is part of why we're hopefully going to be actually fitting for non-constant abundances in our data as well.
Okay, and so we have one more question online.
yes, from Joel Rediger. So what is the statistical significance of the molecule detection of WASP-76b?
Yeah, so these plots down here are actually in terms of statistical significance. So you can kind of just read it off here. It's we detect water and CO at a little bit higher than 4 sigma, and then OH is a bit more of maybe a tentative detection. It's around 3 sigma, but you can see there's a couple other bright spots on that plot. So I guess I would call that one more of a probably detection, but yeah.
Other questions in the room? Oh.
Or I'm gonna trip over the tape. So on the plot that, or on the slide you were just showing with the metallicity numbers, and this is kind of building off of Joel's
Yeah.
question. So you have a M over H of minus 0.19 plus or minus some really large numbers, and then the CO is some really small numbers. So why is that happening?
Yeah, so you can actually see in this corner plot here, we have pretty wide ranges that we get for each of the individual molecular abundances. They're like almost a dex error bars, but they're really strongly correlated with each other. And so the ratio of those is very, very strongly constrained. This was actually found in, there's a published paper by Mclaughlin on Igrin's data of WASP-77, and they found a very similar thing, that it's much easier actually to constrain the ratios of these gases than the absolute amounts.
Okay, we have time for one more question. Yeah, please.
May I have a very quick question? So can you compare the abundance of the planet with the planet host star?
With the host, yeah. So I guess I didn't say this up here, but the host star in this case, I think, is pretty close to solar metallicity and C to O ratio. So it's basically the same comparison. Yeah.
Okay, with that, let's say a big thank you to Megan for her wonderful talk.